This is a lesson on conversions between logarithmic form and exponential form. Very similar to what we did previously in the previous lesson. However, these are more special cases and oddball questions that don't really introduce any new concepts but require us to apply what we looked at earlier. So to start, we will just evaluate a few questions. Now, what we were doing last time was converting from logarithmic to exponential. Now, that is the normal conversion method, because once it's in exponential form, then you can solve pretty much any question if your algebra is strong enough. But these ones are sort of set up a little bit different. They look different. So you're going to get something like this, the log of 81 base 3. And it's not set equal to any variable. So previous lesson would have had log of 81 base 3 is equal to, say, y. And here the y is not there. So it implies that we have a variable. So implies a variable. So in other words, this really means the log of 81 base 3 is equal to y. Now you do want to train yourself not to write this out every time, because the idea is to get good mental math skills with it. But this is what it means. The log of 81 to the base 3 is equal to something. So in other words, 3 to some variable, say y, is equal to 81. And then solve away. You could get a common base, or you could just look at this and by inspection say that the whole thing is equal to 4. And then you've got your answer. But that's how these ones go. They'll just say evaluate, and they imply a variable. And you want to get good at them. You want to be able to, without doing an awful lot of fuss, go from A to B. So I'm just going to off to the side write another one out. If you had, say, the log of 16 base 2, you want to approach this like this. Think 2 to what exponent is equal to 16? The answer is 4. So treat it like that. Let's take a look at a few more. Same thing with this. The log of 64 base 2. Really encourage you not to write it out unless you have to. Think instead, 2 to what exponent is equal to 64? And the answer is 2 to the 6. So therefore the exponent is what we're looking for. So we want to just write that out as 6. So it's taking the log of a value really means finding out the exponent. And that's why when we get into some applications, logarithms become useful. Now this one, number 3, you probably cannot tell by inspection. So I'll note that. Cannot solve by inspection. So if it does not solve easily, set it up. Like this means the base of root 2 to some unknown exponent, which we want is equal to 1 over 16. And it turns into a type 2 exponential equation, like all these ones will. This one's maybe not as straightforward, though. You can, however, break it down to a base of 2. And this becomes 2 to the 1/2 y is equal to 2 to the negative 4. So 1 over 16, 2 to the negative 4. Drop the bases, and you get 1/2 y is equal to negative 4. And when you're solving this, multiply both sides by 2, so you get y is equal to negative 8. So this thing is equal to negative 8. Either write it like this, or just write it negative 8. Either way is fine. But that's the method. You just have to remember that a variable is implied. The exponent is what you're looking for. Now this is kind of an oddball question in its own, because we have the logarithm in the exponent. But it requires us to do what we just did previously. That is, evaluate a logarithm. So the log of 81 base 3, you think 3 to what exponent is 81? The answer is 4. So this becomes 3 to the exponent of 4, which is equal to 81. So what's interesting here, of course, is it took us right back to 81. But you can always solve those exponents first, and then whatever you get in the exponent, raise the base to that. So the question looks worse than it really is. Same thing here. This would be 5 to the exponent. Well, the log of 125 base 5 means 5 to what exponent is 125? Well, 5 squared is 25, 5 cubed is 125, so it's really just equal to 5 to the 3, which is 125. Another series of questions that really work out like the previous ones. You may remember back in the graphing section that we did not find x and y intercepts too often. Occasionally we'd find the x if it was just a horizontal translation, but I consciously avoided them. And the reason for that is that we needed to know what we know now in order to algebraically solve them. So if we have y is equal to the log of x plus 3 base 3 minus 1. Of course, this is a logarithmic function with a translation of 3 units left and 1 unit down. Okay, that's one thing. But to do it algebraically and solve for the intercepts, well, we do what we always do. To go after your y-intercept, we set x equal to 0. And setting x equal to 0 will give us y is equal to the log of base 3. 0 plus 3 is 3 minus 1. Now we have a choice with these. The log of 3 base 3, we just saw that. The log of 3 base 3 is 1. So that's where we evaluate logarithms. And then 1 minus 1, y is equal to 0. Now the other choice would have been to go into exponential form and then solve for it, and we would have got the same thing. But if you can do this, that's a great way. So you just evaluate this particular logarithm. And then your x-intercept, we set y equal to 0. So 0 is equal to the log of x plus 3 base 3 minus 1. Isolate the logarithm as we did before with logarithmic equations. 1 goes to the other side, or simple log equations, and then this is the log of x plus 3 base 3. And express in exponential form. So exponential form would require us to start at the base, go 3 to the 1 is equal to x plus 3. And when you solve for x now by subtracting 3, you will get 0. Now actually, you probably could have made this connection once you got the y-intercept of 0. If the y-intercept of 0, you have to have an x-intercept of 0 too. Now when you look at the graph of these, which I've conveniently graphed, we do have, by inspection, we do have those intercepts of 0, 0. So this one in that respect was easier. But typically you will have to do these algebraically. Let's try another one. Here we have y is equal to the log of x plus 4 base 1/2 minus 3. And we do the same thing. So if you're comfortable with these, stop the tape, stop the video, and solve it on your own, and then compare your answer. So we would get y is equal to the log base 1/2 of 0 plus 4 minus 3. Now I'm going to do this one a little bit different than I did for the previous one. Previously I evaluated the log of 4 base 1/2, which you can do. I'm going to use exponential form on this one, and I'll take the 3 over. Y plus 3 is equal to the log of 4 base 1/2. Just to show that there's more than one way to skin a cat. And when you get it down to this point, your only hope is to put it in exponential form. So we can go no further with logarithms. And once you have it down to a single logarithm, the log of this is equal to something, it works really nicely. 1/2 to the y plus 3 is equal to 4. And we are here again with a type 2 exponential equation. Get a base of 2. So take this 1/2 and write this as 2 to the negative 1 raised to the y plus 3 is equal to 4 being 2 squared. Therefore, 2 to the negative y minus 3 is equal to 2 to the exponent of 2. I'll just take this up here. We can now drop the bases and get negative y minus 3 is equal to 2. So just deal with those exponents. I'm going to take the negative y over to the right side to make it positive. And then I'll subtract 2 from both sides, giving me y is equal to negative 5. And if you wrote this as an ordered pair, you would say x is 0 and y is negative 5 for your y-intercept. So this one was a little more challenging. Now the x-intercept, we as always set the y variable equal to 0 and then solve. So 0 is equal to the log of x plus 4 to the base 1/2 minus 3. Add the 3 on to both sides and we get 3 is equal to the log of x plus 4 base 1/2. So it's so important that you can go into exponential form, because you look at this one and it's a single little logarithm, and how do you solve this? You can't really, unless you're really good. So put it in exponential form and then you just have an equation, and it usually is a type 2. But 1/2 to the 3 is equal to x plus 4, but not always. So for this one, we get 1/2 cubed, so 1/2 times 1/2 times 1/2 is 1 over 8. Subtract the 4 away, and you can either write this as a mixed number or as an improper fraction. I'm just going to think 1/8 minus 3 is going to be negative 3 7/8 is equal to x. So it doesn't make any difference whether you write it as a mixed number or an improper fraction. But it's almost at negative 4. And that would be as an ordered pair. I also have this one graphed, so let's compare our answer with the graph and see if this matches. Remember that you can't graph these yet on your calculator unless they're base 10. So the x-intercept, pretty good, and just about at negative 4. The y-intercept at negative 5. I think we did this one right. Just change gears again and look at simple applications. Now we get into these in a more meaningful way later on when we have a few more tools, really just one more tool. But your simple applications, because logarithms are used very often for really big or really small calculations or values, and that's because the logarithm really is just an exponent, as we've seen earlier in this lesson. When you evaluate a logarithm, you're finding the exponent. So that's good because it makes it huge numbers. We can bring them down to reasonable numbers. Examples of these would be things like Richter scales and decibels, so loudness scales, which we look at later on. But here's another one that's kind of, again, a strange one, doesn't really fit into any categories. And it's based on one of Kepler's formulas. And Johann Kepler, an astronomer, came up with, among other things, a formula like this that relates the length of a year in days for any planet. The length of it would be based on the size of its elliptical orbit. And this 3 log d is equal to 2 log t plus 1.4. I'll note that it's base 10. There's no logarithm, no base given. T is the length of a planet's year in days. And d would be the length of the semi-major axis of the planet's elliptical orbit, adjusted to millions of kilometers. You're probably wondering, semi-major axis, what is that? Later on it gets covered in conic sections, but for your information, if you have an ellipse like this, if you go to the center and then you go to the outside edge, that's what we call the semi-major axis. So it's kind of like the radius, except it wouldn't, because it's an ellipse, not a circle, you don't have a radius that's the same all the way along. So this really is the longest axis that you can get in an ellipse. You don't need to know any of that, because if this is not really part of the section. Later on, of course, you do cover that, though. So here's the question. If the semi-major axis of Jupiter's orbit is 7.78 times 10 to the 8 kilometers, determine the length of its year. So this is another planet further away from the Sun. We do expect its year to be longer than ours. So we go into this formula. 3 log d is equal to 2 log t plus 1.4. And we are aware that we want to solve for the variable t. Do not think too hard. Rather, take this and plug everything in. Now, d, if you take a look at a previous slide, is equal to the semi-major axis, but it's in millions of kilometers. So we take the 7.78 times 10 to the 8, and to divide by a million, you can either divide by a million, or you can divide by 10 to the 6. It doesn't really matter. If you just drive that through your calculator, you will get the same answer. You'll get the right answer. But I'm aware that when we divide powers with the same base, we just subtract the exponent. So this becomes 8 minus 6. So it becomes 7.78 times 10 to the 2. This was not necessary, but it works. And you can even go further by multiplying that 10 to the 2 in. You'll get 778 is equal to d. So I put this in. I go 3 the log of 778 is equal to 2 log t plus 1.4. And then you subtract 1.4. So 3 log 778 minus 1.4 is equal to 2 log t. Now you can do this in a couple steps, or you can do it in one step. I'll do it in one. And I'm going to put this into my calculator. And this is the first time we've had to deal with this. I'm going to divide all this by 2. And this is base 10. So in the calculator, you simply key that in as we have it, as it's written. So 3 log 778. So this is done on the calculator. So remember that the calculator is programmed with base 10, so we can do it. So 3 log 778 minus 1.4, enter. So make sure you press enter at the end of that, or else put a bracket up, because if you do not, your calculator will do the 1.4 and the 2 together. And you should end up with 3.6365, I'll take it to 4 decimals, is equal to the log of t to the base 10. And now, the only way you can solve this will stop a few people, but you just express in exponential form, just like we were doing before. And that becomes 10 to the 3.6365 is equal to t. Now you can use your answer key on your calculator, 10 to the exponent of second answer, which is right there on your negative sign, or just keep the decimals alive on the calculation and you'll be fine. And you'll get t is equal to 4329.8. So Jupiter's year is 4330 if we round to the nearest day. So that is a use of logarithms, and the big concept with it, besides just this conversion into exponential form, is that we can handle base 10 calculators on our calculator. Base 10 equations, on our calculator. But that's it, at least for now. So I will leave you with that, and the next lesson will involve properties of logarithms which make all sorts of other things possible. Thank you for your time.